My name is Eric Kerfoot. I'm the software architect for the Biomedical Engineering Imaging Sciences Department at King's College. So that just means I help with people's software a lot and write software on occasion as well too, and even less occasionally do research. So what we're going to be talking about today is a general overview of software programming languages as they are now. So what ones are we using in current practice and what are the options out there and why different choices would be appropriate depending upon what you're doing, which language to choose for a particular task at any one time. So I was told to expect sort of an audience that isn't familiar with programming, so I'm going to have a very brief overview of what programming actually is, a very brief history lesson of programming languages, and then we'll go over a number of the most popular modern languages and why they're different and what they provide you and which ones you should actually use. And that will be the last little bit. We'll discuss a little bit about what not to use as well too, which is quite helpful at times. So, what is programming? You need to recall that computers are arithmetic or logical machines. So they're just going to do whatever you tell them to do. That really is the key thing about computers. You throw a bit of data in and a few instructions and you turn the crank and that's it. They're not really thinking machines. They're not really brains or anything like that. So we have to define what those operations are, what that logic is we want to apply to our data. Algorithms are the structure that we use to do this, and what an algorithm is for a computer is a well-defined stepwise process for getting some result from some input data. And in our case, well-defined for a computer means mathematically so. All programs are composed of algorithms on some form or another. Even the simplest sort of algorithms like adding two numbers together still constitutes a valid program, and doing more complex things, searching, sorting, doing some really complex numerical work. All those things build upon other algorithms, and those are the pieces that are the building blocks for programs of all sizes. So we'll take a look at a very simple program here. What we're going to do is store one number in one location, store a second number in a second location, and then add them together and store the result in the first location again. So what this looks like in terms of assembly code is these three instructions here. And we program our computers as humans in text format. So here we have the actual text of what a program is going to look like, and we'll see what we do with this very shortly. But this represents these operations in a clear, concise manner. Our first location is just called C. This is a register, which is a temporary location in CPU. We're going to stick 1 into C, and then we're going to stick 2 into D. And then we're going to add C and D together and store that back into C. And that storing component is a bit implicit in the add instruction, but that's what that represents. And the documentation tells you that that's what it is. So this is a very simple program, as I said, very simple algorithm, just add two numbers together. What this demonstrates to us is the first notion is important about programs, and that's sequence. That's the idea of doing one operation after another. So, we store 1 in C, then we store 2 in D, and then we add the two together. And that sequence and that ordering is very important for what actually is going on in our program. And all programs rely upon this notion of sequence because that's how CPUs work. They essentially transition from one state to another. And the next state, of course, relies on the previous state. And so you have that notion of temporality. We also want to have notions of iteration where we want to perform a series of steps multiple times. And so instead of just writing it out multiple times, which is not possible if the number of times is arbitrary anyway, we want to have some way of iterating through that code, of looping through those instructions that we've got. We also need to have this notion of condition where we want to do something based upon some computed condition. Is a number or some other value adhering to some criteria or not? And if it is, then you do one thing. If not, do another thing. We'll see how that's used later on. In assembly language, we represent these as different instructions. So there's instructions for running various tests. There's instructions for controlling where the control flow is. So in our first program, control flow moved from the first move to the second move to the add. And that is where the program is at that particular point in time. And you can move that around. So you can jump to some other points in your program and then continue on execution from there. And that's a very important concept. So if we look at a slightly more complex program here, what this is going to do is store into memory the letters A to J in caps. And the way we are going to do this is to store a value in C that increments over time. So it starts at 0 and goes up to 10. We're going to store an address at D, and what an address is just a numeric location in memory that we're using at any particular time. and that is going to be incremented as well as we move forward through memory. And then we're going to use a temporary value in B, which is going to start off as capital A, which is in ASCII is 65, and then add to that C, and then move that value B into the location memory that is stored in D. So D starts off at position 232, and then what we'll do is store A in 232. And then we increment D, increment C, and then we're going to do a comparison of C against the value 10. And so we're going to see if C is equal to 10. And if it is equal to 10, then that will mean something for us. And if it's not equal to 10, then the next statement, or the next instruction, which is a jump not 0, will be executed. So what will happen here is if C is not equal to 10, if the comparison is not 0, then what will happen is our control flow will jump to where the label is. And so our label is called a loop in this case, and it can be anything you like. But what will happen is after the JNZ instruction, we will jump right up to where we are at the value where we set B for the first time. And so then we'll go through all this code once again. And because we've incremented C and D, we'll then store capital B in the next location, 233. And then we'll do that for C and D and so on and so forth. And we'll loop through these instructions multiple times until C equals 10, at which point in time our jump will not occur. And the control flow just finishes at that point in time and our program is done. So you see all these notions that any other programming language it has to have to be really general purpose. The notion of sequence, of choice in the sense of doing our comparison, and of iteration where we're going to jump through our loop here multiple times. So don't worry if that doesn't make 100% sense just yet, but these are the important concepts that everything is predicated upon. So this is a very simple sort of programming language that we've seen here, and this is something called assembly language for a particular sort of CPU. When you actually want to run this, normally what you do is pass this text to a program called an assembler, and that will take it and convert it into the binary format that CPU actually understands, because CPUs can't actually read the text that you write. It has to be converted into a binary format. And all programs that are compiled for CPUs are in this binary format. So this is relatively convenient because the alternative in the past was to actually write that binary code yourself manually onto either punch tape or punch cards. And this was very, very painful, needless to say. So being able to have something where you can just write text and have something automatically generate binary for you was a huge advance. But still, writing assembly is tedious in and of itself. You have to explain exactly what you want to do and juggle all sorts of notions of memory and locations and temporary spaces everywhere you go. So we eventually want to move on to more advanced languages that will handle more of these things for us. So simple programming languages evolved to automate a lot of the tedious processes. So we saw one of the sort of patterns we have in assembly where we have a loop structure, a label somewhere and then jump someplace else. And we can encapsulate that into a concept and put that into a higher level language that then will generate that code for us and save us a lot of time. So after a while, newer languages evolved, which then needed to use programs called compilers, which would take that language, do some analysis, convert it into assembly, and then hand that off to an assembler to turn it into the final binary form. And then more complex compilers came about that did more useful things for us, did more sanity checks, did more optimizations, might provide certain sorts of runtime environments that aren't just running programs, but actual interpretation environments. All sorts of other newer features that made programming a lot easier, a lot safer, a lot less error prone, and just a lot faster to develop code. And modern languages are built upon all these things and incorporate all sorts of these advanced concepts, but their early heritage still is there. You can still see that in a lot of modern languages. They still have descended genetically from their forebears that came about in the very, very early days of modern computing in the 50s and early 60s. So this is a very, very simplified family tree of programming languages. So our modern ones are at the bottom here, and we'll talk about those. And the very early, the great granddaddies of programming are up here at the top. And this really is accurate. And there's a lot of programming languages in the middle that are just not used anymore. And we'll talk about that a little bit as well, too. So one of the very, very early programming languages that wasn't just assembly was Fortran, specifically what's called nowadays Fortran 1. So this is something that allowed you to define things with more complex statements that could then be translated by the compiler into the instructions that execute them. So for example, doing a statement like this, C equals A plus B, it's very, very simple, but the number of instructions that requires we've already seen earlier, and could be even more if some location C is used someplace else that still needs to be used in the future and requires some juggling around. So Fortran made it a lot easier to write some statements, to write some expressions, and it allowed then a lot of the offboarding of the mental effort onto the compiler itself away from the human. And so that made it a lot easier. There's still a lot of technical constraints though to Fortran. It still was a bit difficult to use, took a bit of learning. There was syntax that needed to be understood. There's a little strange formatting issues that made sense at the time that don't anymore. One of the constraints for the time was that Fortran statements in their entireties had to fit onto punch cards, and that's 80 columns, so that's not very much text. So there are certain constraints like that. There are certain issues of the early compilers being tied to specific hardware that they were built for, and so they weren't portable. You couldn't write a Fortran program and expect it to work anywhere. So that's something that evolved later on. The next generation of languages added new features and did more useful things for us. So Fortran continued to evolve for one. So there's Fortran 2, 3, sort of, and 4. And the modern version of Fortran is called Fortran 2018. But other languages sprung up in very early days that did specific things that weren't necessarily general purpose or were looking more towards more advanced features or looking towards actual research features or research purposes. So one of the early ones was something called SQL or SQL, and this is for doing database access. So this was a language where you can specify what data you wanted, and then it was up to the database to go figure out how to fetch that for you. So that's something more of a functional programming language where you define what you want, as opposed to what we've seen so far with imperative programming languages where you state what you want to do. And so what you want is sort of implicit in that case. But we won't delve into that terribly deeply. There were simulation and science languages. For example, Simula was one of the early ones. Algol was another one as well too. And the very early concepts as these started to pioneer, we still see in modern programming languages. So, these languages aren't used anymore, but their heritage is still there. There were business languages such as COBOL and RPG, and these languages are thoroughly obsolete, but still used in a lot of gigantic administrations and just any sort of bureaucracy. So very large banks, government, insurance companies, they still use these even though they really shouldn't be anymore. They just haven't put the money into translating them to something else, or it's just physically impossible. So these are still around you and they shouldn't be. There's teaching languages such as Pascal. There's also things like Logo, which is sort of a toy language, but anyway, it's out there. There's languages for actually controlling computers themselves directly. So job control languages or languages for scripting behaviors so that you don't have to manually do them. So these are Shell, Bash, which is the Bourne again shell. There's the equivalents on Windows as well too, just called command or PowerShell nowadays. So these were programs to control other programs essentially. There's other research languages for AI, such as Lisp and Scheme and their modern derivatives. For doing logical programming, Prolog and its sort of cousins and relations. And then very basic home use. So BASIC was the kind of thing people got on the very first home computers, and that allowed them to type in programs that looked a lot like assembly, actually. So modern languages, as I said, there's a lot of them out there, and they inherit a lot of the features from their forebears. And there's a lot of languages that are very commonly used. There's a lot that have very niche application. There's a lot that no one uses except the guy who wrote them. So there's a wide range of things out there, but not all of them are necessarily going to be practical for you to use. And so it's good to know which ones are which. To a large degree, you want to look at what languages suit what particular applications they are to be applied to. So some languages are very general purpose and make sense in a lot of places. Some languages are very, very specific to particular application areas. So systems development is a very broad classification of what an application would be. So operating system development or developing drivers or libraries or programs that do low-level things in the computer system that maybe a human doesn't directly interact with, that sort of thing. Applications are more of the things that people actually do interact with. I say consumer software here, but it's more of like the human layer of the computer, the kind of programs you would actually use directly yourself rather than the programs other programs would use. So web development is something like that as well too. So this is the code for the actual websites themselves that you see, for the web applications that run in your browser, but also on the server that it communicates with. So there's those two components of what a web application actually is. There's scientific programming, which is what's of direct interest to us, of course, and that is a very broad category, but that's going to involve very heavyweight computation in one form or another, typically. And also is going to emphasize the idea of experimentation and prototyping. So which language you choose really defined by the technical requirements that you have, what software tools are available that you want to use, what libraries are available, what kind of things are easy to use, what is not going to take up a lot of your time to learn, what kind of languages you can expect your students to learn if that is something you as a supervisor need to be concerned with. And that is something quite important because you don't want to spend too much time learning a tool that is going to be still difficult for you to use. There's also the notion of software maintainability, which is maybe less critical to people who are doing experimental software, but the idea of writing software that can be evolved into the future, can be fixed, can be added to, can be ported to other platforms. These things are not always easy, and the language choice can be very important to whether those things can be done or not. So we come with various sorts of environments that programming languages exist in, but also the sort of development environments that they use. So we looked at compiled languages like Fortran already. You write code in a text format. That text format needs to be translated to something else to run on the CPU. So that requires a compiler. The second way of doing things that actually started very early on with Lisp and other languages was the idea of interpretation, where you would have a separate program that would take the text of your program directly and do whatever the operations are that program defines. So it wouldn't translate it to another form necessarily. It would actually behave as if it were the machine itself. So that's why we call them virtual machines sometimes. And it would actually do whatever the operation is your text defines. So it wouldn't translate it to another format. It would actually go ahead and do it itself. And then it would also be responsible for keeping track of data and temporary values and program state and all the other little things that you would sort of expect a CPU and memory to do for you. So this is a way of having a system that replicates in some way what an actual hardware machine would do. And then, of course, you have hybrids of these two. So you might have some environment where the text of your program might be converted to another format that isn't quite binary, but is something a virtual machine would interpret and do things with. You might have virtual machines that read your program as text or this intermediate format and then compile it to the binary format and then allow it to be executed. So there's hybrids and there's different languages that have different environments and different combinations of these features to them. So moving on, we have sort of a split between these two camps that is sort of true, but not always. And so the answer is complex, and it's just the nature of the beast, I'm afraid. I can't simplify it any more than that. But typically, compiled languages are faster. So Fortran is something that has always been historically thought to be a fast language. We'll talk about that later. Interpreted languages generally are not so fast, but the point is that interpreted language is easier to write typically because it doesn't have the same requirements that compilation imposes on a language. So you don't need to know precisely what a form of data is that you're dealing with. Sometimes you can also write code and then immediately test it. So you don't have to go through that whole write, compile, run, and then back again loop. You can just go ahead and run the program immediately after writing it. And that really does make a difference because sometimes compilation can be very slow. So that is an important aspect to it. But again, it depends on what you're doing, what the technical trade-offs make sense for you. So if speed is important, then you're going to want to consider whether doing interpreted language or not makes sense. Or if you want to look at a hybrid environment. And again, we'll look at what hybrid environments might provide you that can help you get the best of both worlds. So I'm going to just go through what is essentially a very brief catalog of the most popular languages right now. And I have little code snippets. I don't expect you to understand what these are. I'm not going to go into terribly much detail what they do, but this will be for your own reference later on, I suppose. C is arguably the most popular language right now in terms of the number of lines written. I wouldn't think necessarily the number of people writing it, but the amount of code that's actually out there in the wild. So this is a language that is compiled. It is for doing systems development. So operating systems, for example, are written in C. I'm running Windows right now, but a lot of you are writing iOS or are using Linux, and that is written in C to a huge degree. And so this is a language for doing a lot of that work that needs to be done at the low level. So it can interact with hardware directly. It can actually call the operations that you can do in assembly. You can actually have assembly within your C code as well too, for that matter. So it's a very low level programming language, and it's also very fast. So it has very few, as it were, bells and whistles around your code. The actual code that you write can be translated very precisely into a very small amount of assembly with very little extra features around it. And so consequently, the readability of C sometimes approaches assembly in badness, as it were. So that's one of the sort of criticisms of C. It's just as powerful in assembly and just as readable, which is a sarcastic insult, in fact. So our example here just sums the numbers 0 up to 10 inclusively. And this also illustrates the three notions that we talked about. So we have sequence going from where we declare temporary locations called variables, our loop doing our iteration, and our notion of choice where we have here where we're saying we're going to do this loop so long as this condition is true. So we say I is a temporary variable that starts out as 1, and then we add I to some, and then we increment I, and then we keep doing that until I is greater than 10, and then we stop, and then we print our result. So it's doing something very, very similar to what we were looking at already. As I said, C is very super fast. When computation is very critical, that often is the language people will resort to. As I said, it's very common, but it is a bit more difficult to learn. It is something where you do need to be aware of what you're doing at all times. You are directly manipulating memory. So when you want to create an array of values, integers or floats or whatever else, you are using functions that will directly allocate that in memory. And then when you're done with that, that has to be cleaned up by you explicitly. You have to keep track of where your pointers are, which refer to where you are in memory appropriately. And there's just a lot of little things that the language requires you to do to allow just the maintenance work of keeping a program running right. And when you get it wrong, it fails quite spectacularly. We've all seen things like segmentation fault or core dump or things like that. And that's from someone doing something wrong with pointers in C, typically. So it's very powerful. It doesn't help you very much, but it's something that when you do get it right, then it can provide you a significant amount of benefit. C++ is in some ways an evolution of C. It's not quite a superset of C. There is some incompatibilities, but that's very, very, very technical. But it adds this notion of object orientation on top of C. And the idea of objects is you want to combine the concepts of data with the code that operates on that data. So if you want to have a list, for example, that of numbers, you would have an object that stores where that list is in memory, but also stores operations on that list. So counting how many values there are and summing it up, adding or removing numbers in the particular locations. And so the operations on that data and the data itself get packaged up into the same little object. And that is a very useful organizational concept in programming languages. It makes code more modular and reusable. And so that was something that was pioneered in the early days with Simula, where the idea was to write code that would actually be computer simulations of real world objects. So you might have a car object that has a wheel object inside it and things of that sort. And that evolved into more abstract concepts. But C++ was sort of in not the early days, but early 80s, I would say, was going to become the popular way of introducing object orientation to general computing, where before that it was to some degree a research interest topic only. Now, the thing with C++ is that it is notoriously complex. It has a lot of features, and the best rule of thumb with C++ is not to try to use the whole language at once, but to choose a certain subset of those features and ignore others. And that is what people should do when they do write good code. When they don't, and people try and use everything in their toolbox, then it just becomes unreadable, and all sorts of other issues crop up. And with that complexity comes a greater danger. So this is a quote from the creator of C++, where he says that it makes it much easier to blow your whole leg off, and that really is true. So when you get it really wrong with C++, it can be very difficult to fix. But it does provide some other facilities. It does provide ways of doing more error checking, which is helpful. But understanding how to use C++ does require a bit more mental effort and a bit more training on top of C. So looking at our example here, we have a class, which is what we use to define objects with, and that contains two values. We have an integer and a string, which is a string is a string of characters, so text. So we are combining a number with a piece of text into one object, and then there might be multiples of those objects, and they might be floating around in memory, and you might do things with them. All we do here is just create one, set the values, and then print them out to screen. So as I say, these programs don't necessarily do anything useful, and I don't expect these to be instructive in any way. So moving on from C++ into more modern languages that have benefited from that experience with object orientation. One of the early ones that was sort of that next generation along was Java. And this was developed initially as a networking language when the idea of how the internet would work wasn't as fleshed out as it is now. And so there was a lot of new ideas floating around. And one of them was to have a compiled language that you can then distribute that code to people through their browsers. And Java was developed to do that, and then distribute that code through applets. The idea with Java is that it does use a hybrid environment where the code is compiled to something called bytecode, which is not something a CPU can directly understand, but is something that is interpreted by a Java virtual machine. And so that virtual machine might run on your desktop, and it might run in your browser. That was the whole idea. You have different virtual machines for Windows or Mac OS, whatever it was at the time. And you could write the code only once, but run it anywhere. That was the idea with that, and that was quite a good idea at the time. It didn't work out for security reasons and other reasons as well too. But Java is still a very, very popular language. It found a lot of use in business for running a lot of things on the back end. So for doing a lot of server development, Java is seen there quite a bit still nowadays, and for doing other business-oriented software, it's sort of internally. So not so much for software that consumers might use, but for a lot of business-oriented things. In the background, there's a lot of Java. So Java looks a lot like C and C++, and that is not coincidental at all. That is very deliberate. The idea was to present an object-oriented programming language that was a cleaned up version of C++ to a huge degree. So it has a lot of the concepts, but the syntax is a lot simpler. So this example just sums the numbers between 1 and 100. Very similar concept as we saw previously. Microsoft's competitor to Java is called C#, and it's developed after they weren't allowed to use Java, and that's a long story. But anyway, C# looks a lot like Java, which of course looks a lot like C++. It cleans up its feature set in its own way as well too. It also uses kind of a virtual environment and was sort of targeted at things in a very similar way, but its use was never really reached that sort of intention to be used as a networking language like Java was. It is still used a lot in business like Java. It's used a lot for consumer software, especially Windows programming, obviously. So C# is a very ubiquitous language and very popular, and it is very clean and very powerful, it must be said. JavaScript has no relation to Java whatsoever. That was just a marketing gimmick to name it that. It's properly called ECMAScript. But the idea is that it'll be very similar to Java and C# and others. It's a bit easier to write because it doesn't have explicit types, but don't worry about that. But the idea with that is meant to be interpreted by a VM in the browser. So it was explicitly designed as a language to live within a browser rather than being like a standalone systems language. And nowadays you can write standalone programs in JavaScript, and that is done, but it's more typically designed to be run in the browser. So I suspect we're looking at a lot of JavaScript right now in Teams because it's sort of a browsery program. So it's probably using it right now. The idea with JavaScript is you use it with HTML, which describes what the structure of your web pages looks like. And then JavaScript provides the actions, the behaviors. And it will use XML or JSON as the data structure to communicate with servers quite often. So you'll have little JavaScript snippets in your HTML, and you do something or press a button, and then that JavaScript executes. It goes and gets data using JSON, brings it back, and does something with it. That's what it's for, is to provide that behavior to websites. TypeScript is just a cleaned up version of JavaScript, but it's worth mentioning because its popularity is on the rise and you see it mentioned a lot, but they are the same language effectively. Here's an example of JavaScript. So this HTML page will just have a button. You click the button, the JavaScript executes, which is this function here, and that will just change what this paragraph called demo has for text. So it just changes the paragraph. That's all that does. Very simple, but it demonstrates all the concepts. Bash, the Bourne again shell, as I discussed earlier, shells are for controlling other programs. So what this program here does is use another program called echo to write something to screen. And of course, we have our for loop that's doing our kind of iteration once again. But the idea with Bash is that this is a scripting language. So it puts together doing the same sort of processes with other programs, manipulating data, passing them to and from programs, saving data from programs. That's what that's for. For doing periodic operations automatically. That's what Bash is for. So whenever you log in remotely to a Linux machine, for example, almost always you'll get Bash as the program you're going to directly interact with. So whenever you're typing on a console with these operating systems, you're talking to a Bash program somewhere, and that's what that's for. MATLAB is a programming language for doing scientific computing with, essentially. It's another of these interpreted languages, and this was deliberately chosen in its very onset because it was meant to be a language to save students from having to learn Fortran. So it's a lot easier to use MATLAB than Fortran. You don't have to do compilation, all that's done for you. So you can just write things that look a lot more like actual mathematics and expect the environment to sort things out for you. So you can still call Fortran in the background, but it's figuring out how to do that translation for you. MATLAB is the only commercial language that we're looking at here today. Everything else we're looking at is free and open source. So there's a few odd design choices that made sense in the day, but MATLAB is quite common in academia, not so much elsewhere, but it is a language that has its uses and its purpose, its objectives. Python is another interpreted programming language. It has a syntax model that's very strange versus everything else, but it becomes intuitive over time. The idea with Python was initially to be sort of a glue language, something that would just be used to script things together, but it has evolved into a general purpose programming language for doing virtually everything. So web development, application, scientific programming, which is what we use it for a lot. It itself is very slow, but it can interface with compiled code, and we'll talk about that later on as well too, and why that is a very useful thing to have in Python for you as someone who needs to write code that needs to be fast. A lot of libraries for doing scientific computing use Python, and they will call into other libraries that do the actual science for you. So NumPy or NumPy is a language for doing numerical work, and that will use Fortran and C libraries in the back end. For doing machine learning, deep learning, and other artificial intelligence, there's libraries such as PyTorch, which is Python, but it will wrap calls to doing GPU computation using another language called CUDA. Talk about that later on as well too. So here's our example Python. Here we're just going to look for prime numbers between a range of values, so between 900 and 1,000. So it will just look for prime numbers and do that for us. And the important thing about Python, of course, is other languages we're looking at, like C, C++, they use squiggly brackets to denote important blocks of code. Here we use white space, but that's really the bizarre feature of Python people need to get used to. There are a lot of other languages out there. This is very much superficial overview of what there is. There's a lot of languages that do very much the same thing, and which ones you choose are going to really depend upon what makes sense for you. So I won't go through these, but for every sort of application domain, there's a number of languages that are still being used. So it's really important to figure out which language you do want to use. So, it depends upon what your application is, what sort of resources are available, your skill level, the skill level of your students, as well as I suppose. So for fast code, you're probably looking at C or C++. For web development, TypeScript and HTML. For web services, Python or Ruby. Applications, C#, C++, maybe Python. For mobile development, you have a choice for which you want to use for Android or iOS. For scientific programming, I'd say there's nothing better than Python. This is very much the language I like, so that, take that for what it's worth. Looking at a very brief case study, Monai is our deep learning library developed here at KCL in partnership with NVIDIA and many others in our consortium. This is Python, so we deal with almost exclusively at the Python level. There is a bit of compiled code, but it's almost all Python. And this is built on top of PyTorch, which, as I say, is also Python with a lot of in the back end at C++ or CUDA. We do use some C++ for implementing algorithms, but we rely on PyTorch for doing a lot of the heavy lifting for us. So even though our Python is slow, we know in the back end we're using fast code that is compiled for us already, so we don't have to do that compilation. We are also using NumPy, and so is PyTorch. It relies on NumPy directly. And as I say, that uses compiled code in the back end as well too to do fast stuff. So it will use C, C++ for doing arrays of data, using Fortran libraries for doing fast matrix work. VDK is a very popular visualization toolkit, as the acronym implies, written in C++. That's been going on for quite a long time. This relies on OpenGL, which is a C library for doing 3D rendering. And it provides a lot of facilities for visualizing scientific data. And a lot of programs that people perhaps here have used rely on VDK directly. So ITK is another library. ParaView is a GUI environment for rendering meshes and images and such. 3D Slicer, FreeSurfer, a lot of things that a lot of people use in the day-to-day is built on top of VDK. And this is very much a C++ library, and you can use it through C++, but it is probably more palatable through its Python interface. So I'd like to discuss a little bit on what not to use, and this is very much personal opinion and of the things that I dislike. I know a lot of people do use MATLAB, but I strongly discourage it. It is not free, and I think that really is important. It's an odd syntax model. It doesn't have anywhere near the number of libraries Python has, and it's not a general purpose language. Python is general purpose and has libraries for doing all sorts of business related or app development related or any other area of software development. And so if you're writing code for scientific work in Python, you want to plug into something else for, say, doing web serving, you can do that in Python in a couple of lines, literally. Whereas with MATLAB, you really can't. It is painful to do some things in MATLAB. It's really not a transferable skill. So as a student, if you want them to learn skills that they can take and that will help them professionally, MATLAB is not it, but Python really is. There's other languages for doing scientific programming, for example, Julia and R, and they're different in their own particular ways, and there's far less usage of them, even though Julia is growing a little bit these days, but still I would recommend Python over these. For doing high performance work, some people are still using Fortran, and I really do not recommend that whatsoever. Some people still argue that Fortran is the fastest, and I don't agree at all. If you really need to be doing things at the low level, C and C++ is still unbeatable. It still is what you need to do. If you really want to do things really low level and really optimize, you are looking at C. If you really need to do things that are super optimized level, you know, if you know what you're doing and you really need to do something super specialized, assembly is what you need to do. And you can do that in the rubric of C, but not in Fortran, really. Python does have extensions for taking code and compiling it. So Numba, for example, is a library that will take Python code and convert it to C for you. And that can be sometimes very, very fast, and often as fast as you need it to be. Not as fast directly as hand-hacked C, but it will be fast enough. Like you're looking at maybe taking milliseconds instead of hundreds of microseconds, for example, but that that will make very little difference to what you're actually trying to do in a practical sense. But it is there, and it is different. Python is a bizarre hybrid language between Python and C++, even though it relies on Python directly. And again, you can write compiled code that will be very, very fast. And both of these will interface into Python. So you can write your fast code someplace else and then glue it together with slow Python. And it doesn't matter if your Python's slow because you run it only once. So that doesn't really matter. So in terms of that ecosystem that's out there, Python really is super broad and will suit almost everything you want to do. So there's been many languages developed over the last 70 years of really what is the modern computing era. There's a lot of languages that are very old, that aren't used anymore, that really are totally obsolete. There's a lot of languages that are totally obsolete and still used, but that's another story. The vast majority of software development has been done with what is essentially the 10 most popular languages. And popularity is hard to define, but looking at the amount of lines written on sites that store people's code, like GitHub, for example, or looking at Google searches, really, whatever metric you like, there's usually the 10 languages at the top. Python nowadays is number one for a lot of these searches, but of those top 10, virtually all software is written in them. So there's some niche ones that people like to use, but that's sort of, people do that for entertainment purposes, really. The top 10 are really what you want to look at. As I said, Python is an excellent production language because it is general purpose and has language and libraries for doing virtually anything you want to do. And it is also a very good teaching language. And it really is important to have a language that is going to help students learn how to program, as well as being a language that they can take away and actually use for doing practical things. There's a lot of languages that are good for teaching, but are useless in practice, and vice versa. So C++, for example, is a terrible language to teach students on, even though it's used for that quite often. It teaches a lot of bad habits. It gets in the way of the learning process. It doesn't help students. It punishes students very severely sometimes, but it is also a very powerful language once you do learn how to use it, and a very transferable skill. No language is perfect. Even if you have a favorite, someone's going to hate it. So you have to look at languages with a pragmatic eye entirely. What programming language has the technical features you want? What is going to work with you and with your team in terms of what is going to be easy for you to learn, and what is going to be a maintainable software object going forward into the future. So, I mean, the important thing to learn is no language is perfect. One of the sayings is that 90% of everything is crap. What that means is don't fall in love with your tools, and so don't get emotionally wrapped up or emotionally attached to something. Have a sober, pragmatic eye to everything that you're doing and to the choices that you're making when it comes to programming languages.